Okay, so welcome to this first course on algebraic geometry. So let me begin by trying to tell you what algebraic geometry is all about. In its greatest generality, it is trying to study the geometry of the set of common zeros of a bunch of polynomials. Okay, so so let me write that down. So that is in one line what algebraic geometry is. Okay, so so beginning with this, let's try to take the discussion further. So when I say a set of polynomials, of course I should tell you where these polynomials are from. Okay, and then I should also tell you, by that I mean I should tell you these are polynomials in how many variables. Okay, so you must have a fixed number of variables, and then I should also tell you about the coefficients of these polynomials, because of course, for example, we are used to writing polynomials over real numbers, which means polynomials with real coefficients, and for example also with complex coefficients. Okay, or sometimes we also look at polynomials with just integer coefficients. Okay, so the coefficients usually come from a ring. Okay, so so what is happening is that you see in this way the ring of polynomials in several variables over a given ring comes into the picture. Okay, so you see, so what you do is so we pick or rather we are given, I should not say we pick, so we are given a collection of polynomials, let me say a subset of polynomials, so let me write them as f sub alpha of x1 etc xn, S is the set of all polynomials f sub alpha x1 etc xn, and this is each one of these f alphas is a polynomial in a polynomial ring. Okay, so this ring is the commutative ring that consists of polynomials in the variables x1 through xn and with coefficients in the commutative ring R. Okay, so of course I will not repeat this often, we are always going to be worried only about commutative rings, and commutative rings are assumed to be with a unit element, that is with 1, and we will always assume that homomorphisms of commutative rings carry 1 to 1, okay. So so R is a commutative ring with 1, okay, and x1 through xn are variables, n variables, and this is the polynomial ring over R in n variables, and each f sub alpha is a polynomial in this ring, and you take some of these a subset of these polynomials. So this is alpha is some indexing set, let me put it as lambda if you want, okay, in which case I can rather change the index to small lambda for more coherence. So this S is a subset of the ring of polynomials in n variables over R, okay, and we want to study the geometry of the subset Z of S, the set of common zeros of S, and that is defined to be the set of all R1 etc. Rn n tuples of elements of R, okay. So this is just R cross R n times. This is just the Cartesian product of R taken with itself n times. So these are n tuples of elements of R, each Ri is an element of small ri is an element of capital R, such that the if you plug in xi equal to Ri, okay, that is if you substitute for xi the corresponding Ri in this tuple, okay, or in other words if you substitute for the tuple x1 etc. xn the values R1 etc. Rn in that order, then you will get a, and when you evaluate this polynomial, okay, then you will get an element of R, and that has to be 0, and that should happen for every lambda, okay. Then and only then is a point of Rn in this set, okay. So so such that f lambda of R1 etc. Rn is 0 for every lambda belonging to capital lambda, okay. So so maybe this I will just write it as such that, okay. So you see, so basically what is happening is that you already have two objects here. On the one hand you have Rn, which is R cross R n times, okay, and on the other hand you also have the polynomial ring over R in n variables, okay. And what is happening is that I am given a subset S of the polynomial ring, and I am associating to that subset the set of common zeros of that subset, which is a subset of Rn, okay. So and the purpose of algebraic geometry is to study the geometry of this common set of zeros, okay. So this is the general picture. So you can see that already there are two sides to the picture. There is one side which is the geometric side, okay, where you have the space where you are looking at the zeros, okay, and you have here the algebraic side which consists of essentially your looking at the polynomial ring, okay. So you can already see that there is a commutative algebra side and there is an algebraic geometry side. So algebraic geometry is all about going from this to that and that to this based on properties on both sides. For example, you could have properties of this set which are geometric properties, okay, and they would translate into some properties connected on this side, and the properties that are connected on this side are ring theoretic properties, or which may be ring theoretic properties, or therefore they could be ideal theoretic properties, or more generally they could also be module theoretic properties, okay, because modern commutative algebra is not just the study of rings and ideals, but it is also the study of modules, because the notion of a module generalizes the notion of an ideal and also that of a vector space at the same time, and is more versatile, okay. So the properties on this side are geometric properties, the properties on that side are commutative algebra properties, and it's this dictionary, it's setting up this dictionary which is the subject of algebraic geometry, okay. And but of course there are several things that I will have to explain to you. First of all, I haven't so let me write that here. So this is the geometric side, and this is the commutative algebraic side, okay. And in some sense therefore you can say that algebraic geometry and commutative algebra are kind of married to each other in that sense, okay. They are two sides of the same coin, okay. So but then I will have to explain to you what do you mean by the geometry of a subset, okay, because that involves several things. But for example it's at the base level it will involve some topology, and then on top of that it will involve further properties, topological properties, and on top of that it will involve some properties connected with manifold theoretic properties, okay, and so on and so forth, which we will try to explain. But let me at this point go to something else, okay. So first of all, if you give me an equation like this, forget even a set of equations, suppose I give you even a single equation over a ring, okay, it might turn out that this set may be empty, okay. That is the problem. This set, if it is going to be empty, there is nothing interesting to study, because there is nothing to study first of all. So that can happen very easily. For example, if you take the ring R to be real numbers, and if I take something like just one variable, okay, and if I call that variable, so I just take real numbers with one variable x1, and if I take the equation x1 squared plus 1, then you know that it has no zeros in real numbers, okay, because obviously because the zeros are non-real, they are complex, okay. So it's very possible that if you work over a general ring, okay, this particular set, the zero set, can turn out to be empty, and then there is nothing to study, okay. So at this point there is I should say a dichotomy. The subject actually breaks into or rather can be divided into two parts. So there's one question that tells you that if you're going to work over rings such that this is never going to be empty, okay, then of course you have these are good rings over which you can do this kind of study, okay. The other thing is the question that what do you do if this ring doesn't have those properties. So the answer to that is there is an answer to both. So if you so the first question, the first part is you restrict to rings which are algebraically closed fields, okay. If you restrict to rings which are algebraically closed fields, then this set is never empty for a decent collection of polynomials, okay. I will explain what decent means later, and you can do geometry, okay. So that is called variety theory, and that is what is usually done in a first course in algebraic geometry. Then the other thing is, what do you do with a general ring, okay. For example, I would like to work over the integers. For example, questions like Fermat's last theorem, it also involves an equation in 3 variables. It's an equation with coefficients in integers, and then you are trying to ask whether there are non-trivial integer solutions, apart from the easy solutions, okay. Then you also need to solve questions like that, and to solve questions like that, of course, there are equations over integers which do not have solutions. For example, x squared plus 1 equal to 0 is very well an equation with integer coefficients, and it has no solutions in integers. It does not have any solutions even in real numbers, so how can it have solutions even in integers? So the question is, how do you deal with such things? So there is a part of algebraic geometry, a slightly more sophisticated area of algebraic geometry, which deals with such things, and that is called scheme theory. And this scheme theory is a modern language of algebraic geometry, and that is usually what is covered in a second course in algebraic geometry, because it involves far more machinery, okay. But what we will be doing in this course is that we will be safely restricting ourselves to the cases when this set is non-empty, okay. So what I am going to do is I am going to tell you something about solving equations, or rather okay, zeros of equations. So well, so the first thing is, you know, as you would have come across in any first course in algebra, normally usually we start with integers, and then you extend them to rational numbers. Well, of course you could also take natural numbers before this, okay. You can well, maybe I can even do that, it's not a big deal. I can take natural numbers, then I can extend them to integers, then there is a field of rational numbers, then there is a field of real numbers, there is a field of complex numbers. This is how it goes, and every time you have a bigger number system, and that is because essentially you want to solve equations. So number systems become bigger and bigger because you have some equations for which you do not have solutions, so you have to make your set of numbers bigger, okay. So for example, natural numbers, the counting numbers 1 2 3 4 does not have 0, so an equation like x plus 1 equal to 1, which has a solution x equal to 0, will not have a solution here, and an equation like x plus 1 equal to 2, or I mean x plus 1 equal to or rather x plus 2 equal to 1, which is a solution x equal to minus 1, also does not have a solution here, so you are forced to go to integers. And then you can have an equation of integers which does not have a solution in integers, which have a solution only in rational numbers, for example things like 2x equal to 3, it is very well an equation over integers, okay. But the solution is 2x equal to 3, the solution is x equal to 3 by 2, which is a rational number, so you have to extend. So finally what happens is that you see that you come to fields, and you come to field extensions, okay. And the point is that every time you ask the question, when you get a bigger number system, you ask the question, well, if I write a polynomial in that with that coefficients, will the zeros of the polynomial always lie there? And if the answer is yes at some point, then that is called an algebraically closed field, okay. So so the fact is C is an algebraically closed field. Okay, C is an algebraically closed field. So and what does this mean? That is so that is any polynomial in one variable with C coefficients has a 0 in C, okay. So and in fact if a polynomial has a 0, if you call the polynomial as f of x, of course it is one variable, so I should just call it as f of x, where x is the variable, and if it has a 0, which means it has a value lambda such that f of lambda equal to 0, then x minus lambda is a factor of the polynomial, and by the division algorithm you know that the polynomial becomes x minus lambda times another polynomial of lower degree of 1 degree less, okay, and in this way you can continue, and well the polynomial of lower degree that you get, that also will have a 0 in the complex numbers, and you can factor that linear factor out, and if you do like this what it will tell you is that finally any polynomial can be completely split into linear factors, okay, that is what it says, and this is the property of the field of complex numbers which makes it algebraically closed, and in general this is a definition of what an algebraically closed field is. An algebraically closed field is a field such that you take any single polynomial in one variable over that field, then all its zeros are in that field. That it means that you can find all the zeros in the field itself, you do not have to extend the field, you do not have to extend your number system to something bigger where you will get the zeros, okay. So basically what it tells you is that if you are, so what it tells you, if you go back to our setup, what it tells you is that if I take R equal to C, if I take my ring to be C which is in fact a field, okay, and if I take n equal to 1 then I have C here, and here I will have C of x, okay, polynomial ring in one variable, and then it tells you that you give me if you give me a single polynomial, if this S, if the set S is a single polynomial, then the 0 set of that is non-empty. In fact it will have the number of zeros will be equal to the degree of the polynomial, but of course you have to count the zeros with multiplicity, okay, you have to count the zeros with multiplicity. After all the polynomial may be x minus 1 to the power of 5, okay, and then if you want to count the zeros with multiplicity then you can think of them as 5 zeros, but if you think of it as a subset here you get only one point, namely the point 1, okay. So what this tells you is if you are working on an algebraically closed field and there is only one variable involved and you are looking at only one polynomial, then you end up in a situation where this set is non-empty, okay. Now the question is, mind you, our original question is we are not looking at a single polynomial, we are looking at a bunch of polynomials, okay, and this need not even be finite, this collection of polynomials need not even be finite, and not only that we are not looking at a polynomial in one variable, we are looking at a polynomial in several variables, okay. What the algebraic closure property tells you is that if you are looking at a polynomial in one variable and if your coefficient ring is an algebraically closed field, then if you look at the zeros of a single polynomial then it is not going to be empty, okay, but we want something very very general to happen, okay. The answer to that is, so you might expect that should you put some more conditions than just the field being algebraically closed for such a thing to happen, and the answer is no. The amazing answer is yes. The amazing answer is this itself will ensure that so long as this set S is good in a decent way, if R is an algebraically closed field then Z of S can never be empty, okay, and this is a very deep fact, and this is called this is one form of the Hilbert-Nullstellensatz ansatz, okay. So let me write that down. So fact, so if we take for R an algebraically closed field, then for f in Rx, Z of f is non-empty, of course provided f is non-constant. Of course, you know, when you are looking at zeros of a polynomial, certainly you are not looking at a constant polynomial, okay. What that means is if you are looking at a constant polynomial, if that constant is non-zero, then there are no zeros, and if that constant is 0, then the whole space satisfies the condition. Okay. So if you take a non-zero constant and consider that as a polynomial, then it has no zeros, so its 0 set is empty. If you take 0 as a constant polynomial, then its 0 set is a whole space. Okay. So what it says is that if you take for R an algebraically closed field and this set S to be a singleton consisting of only one polynomial, which is of course non-constant, then the 0 set is non-empty. So you ensure that this is non-empty, so you can do some geometry. Okay. But then here is the important thing. So what we want is not for one variable x, but we want it for several variables, and we don't want it for a single polynomial in several variables, but we want it for a whole collection of polynomials in several variables. Okay. So that is our deep requirement, and that's what the Nullstellensatz, as it is called, Hilbert's Nullstellensatz, that's what it promises. So let me write the following down. So first let me say the following thing. Suppose so here is a very simple, let me call it a lemma. I'll write a very simple lemma. If the set S is such that that does not exist a finite subset let me write f lambda 1 f sub lambda m and polynomials g lambda 1 g lambda m in the polynomial ring such that sigma f lambda I g lambda I is equal to 1, I equal to 1 to m, then so I should say and only then so I should say the following thing. So there is one part of the lemma which is very trivial, there is the other part of the lemma which is actually the Nullstellensatz when R is an algebraically closed field. So let me say that correctly. I have to modify this statement a little bit. So let me make a small modification. If the set S is such that Z of S is non-empty, then there cannot exist a finite subset such that this is equal to 1. So this is a statement. Okay. So I am saying that suppose so you see the whole point is the following. The whole point is we are trying to study this set of common zeros. Okay. We don't want that to be empty. You don't want that to be empty, and the statement I am making is that if it is non-empty, then no finite subset of S can generate 1. Okay, no finite subset of S can generate 1. That means you cannot get finitely many elements of S and finitely many polynomials from the ring of which this capital S is a subset of, such that you multiply them and then add them, you get 1. That cannot happen. That is obvious, because you see if the 0 set is non-empty, that means there is a value small r1 etc small rn in the 0 set, and this value small r1 etc small rn, when you substitute it in each of these f lambdas, it is going to vanish. Okay. So in particular, if I substitute it in this relation on the left side, okay, the left side is going to vanish and I will get 0 equal to 1, and in a ring if 0 equal to 1 then the ring is a 0 ring, okay. It has only one element which is 0 ring, and certainly we are not interested in working with a 0 ring, okay. So if the ring is not the 0 ring, then what this tells you is that if the 0 set is non-empty, this can never happen, okay. It's obvious, this is a very simple thing, okay. But the converse to this holds when the ring is an algebraically closed field is one form of the Hilbert-Nullstellensatz ansatz. So let me write that the converse is true if R is an algebraically closed field and that is one form of the Hilbert-Nullstellensatz ansatz. So maybe, so let me keep it like this, let me not state it. The converse will be that if the subset S, if R is an algebraically closed field and if the subset S of polynomials in the polynomial ring over R in n variables is such that no finite subset of that can generate 1, then the 0 set defined by that subset is non-empty, okay. That is one form of the Nullstellensatz ansatz, which is usually called the weak form of the Nullstellensatz ansatz, okay. So of the Nullstellensatz ansatz, so maybe I will write it down. So let so what is that? So if K is an algebraically closed field, and S is a subset of polynomials over K in n variables, of course small n is greater than or equal to 1, okay, then such that there does not exist a finite subset let me write f1 etc fm in S and polynomials. So let me continue here. G1 etc Gm, so this is M, again in the same ring such that sigma fi gi is equal to 1, I equal to 1 to m, then the 0 set defined by S in Kn is non-empty. You can find solutions. See, what you must understand is that the Hilbert-Nullstellensatz ansatz is a grand generalization of the property of being algebraically closed. You know, if I put in the Hilbert-Nullstellensatz ansatz, if I put small n equal to 1, then I am looking at polynomials only in one variable, and if I take the subset S, capital S, to be a singleton set, okay, then this statement is obviously true if for an algebraically closed field. See, what you must understand is Hilbert's Nullstellensatz ansatz, when you put n equal to 1, is true just by the definition of algebraically closed field, because what happens when you put n equal to 1 and when you take the set S to be a singleton consisting of only one polynomial, and then if you have this condition, that then this condition will become that polynomial multiplied by no other polynomial gives you 1, which is the same as saying that that polynomial is non-constant. Okay, then you are saying that the zeros of that polynomial in k1, which is just k, exist. So you are just saying that every polynomial has a 0, which is the definition of what an algebraically closed field is. So what you must understand is that Hilbert-Null-Stellan-Schwarz is a grand generalization of the definition of algebraically closed, and it's a very important theorem, and this is a theorem that guarantees that if you are working over algebraically closed fields, then you can really do geometry. Okay, so and this is called the weak form. We will come to the stronger form later on. Okay, and I will see later on if I can hint at a proof of the Hilbert-Null-Stellan-Schwarz. Usually a proof of the Null-Stellan-Schwarz is given in a course in commutative algebra, but then there is also a way of looking at that proof completely in algebraic geometric terms. So this is something that keeps happening, that you must always keep at the back of your mind. There are many things that can be said in this on the language on this side, which is the algebraic geometry language, and there are the same things can be said with the language on this side, which is the language of commutative rings and modules and ideals and things like that. Okay, so proof here will involve ring theoretic arguments, ideals and homomorphisms and modules and things like that, whereas the same proof, when you translate it here, it will have geometric meaning, and it's trying to go from one to the other that really enriches both the sides. Okay, so okay, so incidentally I should tell you what this Null-Stellan-Schwarz is. So this is German. I mean, Hilbert was a German mathematician, and of course one of the greatest of all time, and Null stands for 0 and Stelle stands for position or point, and Schwarz means theorem or statement. So it's actually, so if you translate it properly, it means Hilbert's theorem on zeros of polynomials, of a bunch of polynomials. Okay, fine. So okay, so what we are going to do is, so from now on we will always work over an algebraically closed field K. That is we take R equal to K. So if you want, for convenience, you can even think of the algebraically closed field as complex numbers, so that if it makes it easier for you to think about things and visualize things. Okay, so what we are going to do, so our picture becomes so our picture goes from that generality into something more concrete. So we have the following picture. On the commutative algebra side, we have K of x1 etc. xn. This is the polynomial ring in n variables, and on the geometric side we have Kn, which is k cross k cross k n times. Okay, now well, how do you think of Kn? You are used to Kn from linear algebra. I mean, always the simplest way one would look at it is as a vector space of dimension n. Okay, for people who have done module theory, Rn can be thought of as the n-dimensional free module over R. Okay, so in fact we don't use the word dimension for modules. So I should amend my statement to Rn is the free module of rank n over R. Okay, so dimension is usually reserved for fields. So Kn is an n-dimensional vector space over K. A module over a field is a vector space, okay. So but it is not the vector space properties we are interested in. So you see the vector space, the properties of vector space are you have the 0 vector, and then you know you have addition of vectors and so on and so forth. So in that sense you know the vector space, studying the vector space properties is literally studying linear algebra, but that is not what we are interested in. What we are interested in is actually trying to study the points of the space, okay, without any regard to the vector properties, okay. So it means that all points of the space are alike. I mean, if you take the plane and throw away the vector space structure, that means you take the plane, and how do you get the vector space structure? You have to first have an origin, because for a vector you need an initial point and then you need a terminal point. So normally what we do is we have an origin, and every other point to every other point we associate the vector which starts at the origin and goes to that point. We call it the position vector of that point, and then we study all these position vectors and add them as usual with parallelogram law and then so on and so forth. But what we are going to do now is not worry about doing all this. We are going to think of all points as equal, as one and the same. So think of Kn, but do not think of the axis, do not think of the origin as the origin of the vector. So you just think of it, for example, if n is equal to 2, think of the plane but without the 2 axis. There is a point called the origin, but that point is not you don't try to, for every other point you don't try to draw a position vector and think of it as a vector. So you know this process of trying to think of Kn as a space not of points but not as a space of vectors is what makes it into what is called an affine space, okay. So the affine space Kn is different from the vector space Kn. In the affine space we are only worried about the points, not about the vectors, okay. So you will see often in algebraic geometry people use the word affine, and that is the whole point, okay. So the first important thing is don't ever think of these as vectors, okay, though it is a vector space of dimension n, but that is not what we want, right. So so this is the affine space literally, and given a subset S you get the 0 set of yeah, that is right here. So here is our this is the picture we are going to look at, and we are going to see what is there on both sides, okay. So the first thing that I am going to do is so that brings us to the following question. What are we going to do with this set? We have thrown away the vector space structure. It is just a set. Now what are you going to do with it? So the first step is to give it a topology, okay, and that topology is called the S30 topology, okay. So I will explain what that topology is. So so let me write that. So let me write the following thing: Kn along with the S30 topology is called affine n space over K and denoted an K, okay. So the first thing that we do to get some geometry on the left side is first of all have at least a topological space, okay. So we make Kn into a topological space. What does that mean? It means that you have to specify a topology on it, and specifying a topology on it means what? You try to give a collection of subsets which you may call as open subsets, and this collection has to satisfy the axioms for a topology. And what are the axioms for a topology? The whole space should be an open set, the null set which is the empty set should be an open set, an arbitrary union of open sets should be open, a finite intersection of open sets must be open. So these are the 4 conditions for a collection of subsets of a topology of a space or of a set to make it into a topological space, okay. So I'll have to explain what the open sets are, okay. But then you know when you go to topology there are two ways to approaching a topology. One way is by open sets, the other way is by using closed sets, okay, because closed sets are just complements of open sets. So I can also give a topology on a set by giving a collection of subsets called closed sets, but then the conditions will be complementary, okay, because of De Morgan's laws. So the conditions will be that the whole space is a closed set, then the empty set, that is the null set, is a closed set. Any, if you take a finite collection of closed sets, their union is again a closed set, okay, and if you take an arbitrary collection of closed sets, their intersection is again a closed set. These are just translations using De Morgan's laws for the corresponding axioms for open sets. So basically what I will have to do is that I have to tell you either I should either give you a collection of open sets or I should give you a collection of closed sets which satisfy the corresponding axioms. And what happens in geometry is that it's easier to begin with by looking at collections of closed sets, and guess what are going to be the closed sets? The closed sets are going to be just common zeros of functions of this type. So you see the idea is the following: you look at this space, look at Kn, think of these as functions on Kn. Of course you take any polynomial here and you take a point here. If you evaluate the polynomial at that point, you get a value. So certainly a polynomial, the elements here which are polynomials here are certainly functions on this space, and what you do is you call a subset here to be closed if it is in the zero locus, common zero locus of a bunch of polynomial functions, which is exactly what this is, okay. So the moral of the story is that if you declare subsets of Kn of this form, zero loci of a bunch of polynomials, common zero loci of a bunch of polynomials, call them as closed sets, then you get the Zariski topology. That makes this Kn into Zariski topology. So what that will tell you is that what are the open sets? The open sets will be loci where functions do not vanish. The loci where the functions vanish, for example the locus where a single function vanishes is a closed set, and the complement of that locus where the single function does not vanish is an open set, okay. And this is in tune with our common sense, okay, because if you take a real valued function on some subset of Rn, or you take a complex valued function with on a subset of n dimensional complex space Cn, then the set of points where the function takes the value 0 is going to be a closed set provided the function is a continuous function, because it is the inverse, a point is always a closed subset, and if a function is continuous the inverse image of a closed subset is closed. Therefore the set of points where the function is 0 is exactly the inverse image of the point which is 0, and that has to be closed, okay. So it agrees with our usual intuition. So the idea is to give the Zariski topology in that way, okay. So we will look at that in more detail in the next lecture.